your mass spectrum is helpful for figuring out the fragments, and it's sometimes helpful for figuring out the number of carbons, yeah? So mass spectrum you can start off with, but it's not going to give you much information at the beginning. It'll give you an estimate about the number of carbons, which is what it's good for, yeah? So first things first, notice how the molecular iron peak is 80. So that's 80. This is 85. So this has to be 86. Okay, so you want to get that information out. It's not useful now, but you want to check the structure you have at the end to make sure it has a atomic mass of 86. Okay, there is a peak at 43, which my memory has left from me. 43, sorry. 43 is a propyl fragment. Yeah, so it's CH3, CH2, CH2. Now, this doesn't tell you anything about the structure. However, it does give you enough information for you to know that your compound has at least 3 carbons inside of it. Okay, so your technique for this kind of question, go through and analyze each spectrum one by one. Analyze it just all over the page and then worry about getting it nice into words afterwards, because you're going to have to go back and forth before you can make a nice 7-mark answer, yeah? Now, the other thing is this. We've talked a lot about like keeping your cool in the exam and things like that as well. This is the kind of question you want to do it for. Please trust me, do your practice questions, a lot of them, before the HSC and before your trials. You will have plenty of time. Okay, even by the way, even when you're doing your practice questions at home and you feel like you're not getting enough time, the exam adrenaline hits different on the actual exam day. Okay, I know we talk about doing practice questions. I know we talk about doing practice exams and modeling it, but that's the closest you can get to modeling the exam. But nothing is like actually taking the exam. So in the exam, you're going to be a lot more attentive than you think you are. You're going to be writing a lot faster than you think you are. Yeah, so you're going to have more time than you would when you're doing practice exams at home. So with these 7-8 mark questions, don't feel time pressured to obviously check the time. If you're really close to it, then you should speed up, but don't have a false sense of not having enough time. There will be plenty of time, yeah? So do this nice and slowly because it's a valuable question. You want to get it right. So that's all the information you pretty much get out of it for now. And then there's also a signal at 57, and then there's a signal at 71. So from our notes, 57 is a butyl, which is which is 4 carbons. And then if we want to check a pentyl fragment, so 12 by 5 for 5 carbons, and then how many hydrogens would there be? So there'll be 2 on 4. So 2 by 4 plus 3 on 3 hydrogens on the very last carbon. That's going to be 2 by 4 for the non-terminal carbons, and then 3 hydrogens for the terminal carbon. That's going to be 71. Okay, so that fits that signal right there. So this is actually a C5 fragment. Yeah, so your mass spectrum allows you to inch a little bit closer, figure out how many carbons there might be. Okay, and then if you add another 12 onto 71, you get to 83. Okay, but chances are the molecule they're making you look for is not going to be a regular alkane. So you need to make space for things like oxygen and things like that, yeah? So the chance of there being 6 carbons is very unlikely. There's probably only 5, but just we know that it's somewhere within the 5 to 6 region. That's all you need to know for now, yeah? So that's all you get out of your mass spectrum at the start. You go back to your mass spectrum at the end. So that's your mass spectrum. For infrared, you have a really small signal at 3000. It's not a broad signal, which tells you that it's not an alcohol. Okay, so not broad, which means not an alcohol, not an acid. The other thing you can get that's close to 3000 is an amine, which is above 3,000 though. It's 3,300, so it's not going to be an amine either. The only other thing left is your CH, which means that peak is really not useful. It's really frustrating when you get that peak. I don't know if you guys have dealt with it yet, but this really narrow peak at 3,000 is just a CH, so that's not useful. Normally though, okay, as you do more questions, you realize if there's a CH there, there's probably another signal close to your fingerprint region, but a little bit out of it. Yeah. So this one here is 1,500. This one here is 2,000. So this peak right here is about 1,700. Okay. So if you go to your data sheet, 1,700, the only one that 1,700 fits within is 1,680 to 1,750, which is your carbon-oxygen double bond. So if we go back to the question book, that's going to be C00. Okay, so that tells you that it's probably an aldehyde, might be a ketone, and not going to be an ester, okay? Because an ester has this as well as this, the carbon-oxygen single bond as well. You don't have a peak for that. They told you to ignore this region, so it's only going to be carbon-oxygen double bond. So that's what you get out of that, okay? Now, because there's an oxygen, that definitely tells you there's not going to be 6 carbons. Because if there's 6 carbons, 5 carbon chain is already 71, okay? You can't add another hydrogen, you can't add another carbon to that and then add another oxygen because it's going to go above 85, okay? So that sort of confirms to you that there's probably going to be 5 carbons. Obviously, be flexible because it might change, and then 1 oxygen, and then however many hydrogens after that. Can I get a thumbs up to confirm that that makes sense so far, sort of the process behind this? Grace, all good? Any questions, please unmute yourself straight away. Good, awesome. That's the process so far, okay? And then your proton NMR. You have a septet, you have a singlet, and you have a doublet, okay? So, Grace, if there's a septet, how many neighbors does that hydrogen have?
7.
Septet is 7, yeah? How many neighbors would it have though, sorry?
Oh, 6.
Yep, good, okay. Because the rule that we use for neighbors is n+1. So n+1 is going to be the number of splits, and n is the number of neighbors. So however many splits there are, -1 from that to get your number of neighbors. And then Jen, this one is a singlet, which means how many neighbors does those 3 hydrogens have?
0.
0. And what about the doublet?
1.
Good, okay. So proton NMR is really useful. I really like it. Okay, carbon-13 NMR is second one, but it doesn't have splitting, so it's not as useful. The splitting helps you see how many neighbors there are, and it helps you position your hydrogens around your carbon. Yeah. So you have 1 hydrogen that's bonded to 6 carbons. Sorry, you have 1 hydrogen that has 6 neighbors, and then you have 3 hydrogens that has no neighbors, and then you have 6 hydrogens that have 1 neighbor. Now, normally when something has 6 neighbors, it tends to be between 2 methyls. Okay, so you just want to see trends. Now, remember with this stuff, yeah, guys, you want to look for possibilities, but you don't want to fix yourself into one structure until you've confirmed everything, yeah? Normally, when there's a septet, and there's 6 neighbors, that hydrogen tends to be between 2 methyls, yeah? The other thing to keep in mind is as you go through it one by one, you can combine the information as you go, yeah? So notice how we started off with mass spec and then said that there was 5 to 6 carbons, and then we said there's an oxygen here, so it's probably not going to be 6 carbons. We'll confirm that it's 5. Okay, down here, now we know that there's some hydrogens that don't have any neighbors and things like that, okay? Also, that's just in terms of your splitting. We also have to look at it in terms of downfield and upfield, which is chemical shift, yeah? The septet is really downfield, okay? So it's only 1 hydrogen, okay? It's only 1 hydrogen, but it has 6 neighbors. That 1 hydrogen is really downfield, which means this tells me that this is the hydrogen that's bonded to the carbon, that's bonded to my oxygen. Okay, that hydrogen is probably bonded to the carbon, that's double bonded to the oxygen. Now, a question to challenge you guys, okay? If this is true, okay, what must my compound be? I have a double bond, my hydrogen's probably bonded to the carbon with the double bond. What family of organic compound must it be if what we have so far is true? You guys know this.
Is it an aldehyde?
Good. Why is it an aldehyde, Jen?
Because it's bonded to a H, so it has to be like at the end.
Good. Okay. We're done. The only possibility is that it has the H at the end. Now, the reason for that is because if it was a ketone, that means it's non-terminal. So technically, most of the signals would have to be upfield because you can't have an extra hydrogen because there's already 2, 3, and 4 bonds here. So it's probably going to be an aldehyde. Once again, be flexible until you can confirm that that's true. Okay. But probably an aldehyde. So that's the confirmation there. Now, okay, we've said that it's probably an aldehyde, and then because it's a septet, it has to be bonded to 2 methyls, okay, which doesn't really work. Okay, it doesn't work because you already have 2 bonds with your oxygen, and then if it is an aldehyde, there's another bond here, so you only have space for 1 more bond. Yeah, you can't attach 2 methyls to it. So you have to watch out. Yeah, maybe that oxygen is electronegative enough that even if the hydrogen's not directly bonded to it, it's bonded to the carbon next to it, that it's still able to make it downfield. That's a possibility. Okay, so let's watch out for that. If it's a singlet, it has no neighbors, so we have to put it in a place where the carbon that it's bonded to has no carbon. What that tells me, okay, if my carbonyl functional group has a hydrogen on the end of it, then there's really no other way I can make a structure of a molecule with no neighbors. Yeah, because if it's an aldehyde, there's going to be neighbors everywhere. Okay, the only way I don't have a neighbor is by making use of this somehow, which sort of tells me that this singlet right here, it's gonna look something like this. Yeah, because this is 3 hydrogens and the carbon that it's bonded to has no hydrogens on it. So this information sort of tells me that it might end up being an aldehyde. So also, because the fact that I can't add 2 methyls sort of tells me that it's probably not going to be an aldehyde either. Okay, so shift and adjust your predictions as you go. Can I get a thumbs up to confirm that that one makes sense as well? It's a singlet, it has 3 hydrogens, it's probably a methyl, and because it has no neighbors, it's probably bonded to a carbonyl. Yeah, so that's sort of the prediction so far. So just watch out for that. Okay, so this one, let's just make a note here. Probably bonded to non-terminal COO. Okay, and then this one's a doublet and it's 6. So there are 6 hydrogens with the same environment. Now, 6 hydrogens with the same environment, there can only be a maximum of 3 hydrogens on each carbon. What that tells me, okay, so just to reiterate, yeah, unless it's methane, you only have a maximum of 3 hydrogens on a carbon, which means if there's 6 hydrogens that show the same signal, that probably tells me that there's 2 methyl groups that have the same environment. Can I get a thumbs up to confirm that makes sense as well? 6 hydrogens, same chemical environment, maximum 3, which probably means that there's 2 different methyl groups that have the same chemical environment that show the same signal. Awesome. So that's your proton NMR. That's what we've digested from it so far. And then your carbon-13, you actually have 4 signals this time. There's one that's really downfield. That's obviously going to be the one with the carbonyl, and then everything else is super upfield. Okay. And then there's one that's really high up, which is probably corresponding to the 2 carbons inside of the methyl group here. Okay. Now, you don't get HNMR data in your data sheet, but you do get carbon-13 data in your data sheet. Okay, so I don't find it particularly useful sometimes, but we can have a look and see if it works. It's in terms of interpreting the structure, I don't find the information on carbon-13 NMR in your data sheet very necessary. Sometimes it is, but you want to refer to it anyway in your 7-mark answer, even though it's not necessary for the structure. Okay, so let's just see. We have a signal at 20, we have a signal at about 29, we have a signal at about 40, and this one is over 200, yeah? So let's pop over to our data sheet super quickly. Above 200 is an aldehyde or ketone. We've already confirmed that, but you can pop that into your answer anyway. And then for the 20s and the 20s to 40s, that's a non-terminal carbon, non-terminal carbonyl. Okay, so all of your signals, we had 20, we had 29, and then we had 40, the ones that were upfield. So they're all within 20 to 50. We've already confirmed that there's no nitrogen, so this one's out of the picture. Okay, so this also confirms that it's a ketone. Okay, so it was a good hunch earlier that it might be an aldehyde, but as you go, you have to be flexible. We've confirmed that it's a ketone. Okay, so that's how you use your carbon-13 NMR data. So notice how we figured that out without looking at the data sheet, but since the data sheet is there, you want to refer to it in your answer anyway. So that's what we've confirmed, yeah? It has to be a ketone, okay? Which means there has to be a carbon here and there has to be a carbon here. You can't add another carbon, so this is the only way it'll work, okay? So that's what we have so far, yeah? It has to be a ketone, and a ketone is when the carbonyl is in a non-terminal carbon, so you have to have a carbon on the left and you have to have a carbon on the right. So that's what we've got out of your carbon-13 NMR, yeah? And then we got the carbon oxygen double bond from your infrared spectrum, so we can cancel that out now as well. So we've used that information. So proton NMR is going to be your most useful one. And then once you've figured out your structure, you go back to your mass spectrum, make sure it would give the same fragments you're expecting. So first things first, you have a really downfield single hydrogen. You have a single hydrogen that's really downfield, okay? And it's a septet, which means it's bonded to 6 hydrogens. Oh, sorry, it has 6 neighboring hydrogens. So because it's a single hydrogen and it's really downfield, but originally we said it's an aldehyde, now we've confirmed that it's not, which means that second best thing is that hydrogen is on the carbon next to the carbon in the double bond. Okay, so just to reiterate, we said that because it's really downfield, it's probably bonded to the carbon in the double bond with the oxygen. But now that we've confirmed that it's a ketone, the next best thing, the only way it's so downfield is that it's bonded to the carbon that's bonded to the carbon in the functional group. Can I get a thumbs up if that makes sense? We can't directly attach it to this carbon, so the next best thing is to put it on the carbon next to it. Yes, good, awesome, thanks guys. Okay, so I'm going to put a hydrogen here. Now I'm confused. How come I only put 1 hydrogen? Okay, but here's the thing, yeah? It's only 1 hydrogen. I'll just follow my structure. It's fine. It's only 1 hydrogen. But then we also know because it's divided into a septet, it has to be bonded to 2 methyl groups, which means my structure is going to probably look something like that. Okay, so I put 1 hydrogen next to the next carbon after I confirm that it's a ketone. And then because it's divided into a septet, this hydrogen has 6 neighbors. The neighbors are on the carbons next to it. So these are the carbons next to it, and there's 6. So that's how I put my methyls in. Can I get a thumbs up if that makes sense as well? I'm going to ask for a lot of thumbs up here to make sure that we're following along. Does that make sense too? Good. Okay, so I've made use. I've made use. I don't know if you guys are having fun. Okay, keep your thumbs up if you're having fun, because this is my favorite part of the year 12 syllabus. Okay, This is great. Okay. I hope I got it right in my HSC. I don't even know if I got it right. You know, you have to pay for your own paper. God dang. So, yeah, this is a fun question. Anyway, when you get into university, apparently you have to pay for your own transcript as well, which is like the proof that you did your degree. Blows my mind, honestly. Anyway, so that's your septet. Okay, and then you have your singlet, which has no neighbors, but it has that singlet, 3 hydrogens made up that signal, which means because it's a singlet, it has no neighbors, okay, which means the carbon that my carbon is attached to, so I'm the 3 hydrogens, yeah, but even though I'm 3 hydrogens, I only produce a singlet, so I don't have any splitting, which means I have no neighbors, which means my carbon, so I'm the 3 hydrogens, my carbon that I'm bonded to is bonded to a carbon with no neighbors. Okay, you've filled out your structure enough now to see that the carbon in the double bond is the one that has no hydrogens because it's a non-terminal carbon. It's a non-terminal carbonyl functional group, which means my 3 hydrogens, it's probably a methyl, and it's probably a methyl that's bonded to my double bond, which means it's probably over here. Okay, can I get a thumbs up if that makes sense as well? I'm a singlet, no neighbors, which means I'm probably bonded to the carbon with the oxygen, and because I'm 3, that probably tells me I'm a methyl. Okay, so I seem to have completed my structure now, yeah? But let's just confirm that there's no more carbons, because remember, when I did my original one, I just added a 1 to the left and to the right. I wasn't confident that the carbon chain doesn't keep on going, so let's just check, yeah? My last signal is a doublet with 6 hydrogens. We said that that's 2 methyls. We added 2 methyls at the start. Okay. And then that methyl, those methyls are bonded to a carbon with 1 hydrogen. So a doublet means 1 neighbor. So that's confirmed our structure as well. Okay, so that's all good. So we've used up our carbon-13. We've used up our proton NMR. And we've used up our infrared. Now what we're going to do is go back and confirm our mass spectrum, yeah? 5 carbons, like we originally said. 1, 2, 3, 4, 5. Okay, good. So, you have a peak. Oh, and first things first, just check your molecular ion peak, 86. Okay, so let's just check that one first before we check the fragments. Just check the overall molecule. So you have, just to check the molecular ion peak, you have 5 carbons in total. And remember, mass spectrum use whole numbers, not relative atomic mass in your periodic table. So it's just going to be 5 by 12, not 5 by 12.01. And then plus, you have 1 oxygen. So that's going to be plus 16. And then you have 3, 6, 9, 10 hydrogens. Plus 16 plus 3 by, plus 1 by 10. So 1 by 10. And then if I pop this into the calculator, 5 by 12 gives me 60, plus 16 plus 10 is 60, 70, 86. Okay, so I've confirmed my mass spectrum. Okay, now at this point, we're pretty confident that it'll match the mass spectrum, just because mass spectrum gives you a lot more generalized information than proton NMR and carbon-13 NMR does. So if your answer fits proton and carbon-13 NMR, it's a pretty done deal that that's going to be the answer, because mass spectrum, things like the 43 fragment with the propyl and stuff like that, a lot of different things can have propyl. So, but it's good to confirm anyway, and it's a 7-mark question, so you want to have as much detail in there as possible. So let's just check. 43 comes from 3 carbons and 3, 5, 7 hydrogens. Okay. And you get that here. So it's not your regular straight chain CH3, CH2, CH2. In this case, you get 3 carbons, and 7 hydrogens, yeah? So it's just a different fragment. So 43 is generally CH3, CH2, CH2. Just keep in mind it's not going to always be in that structure. But now you've confirmed that the 43 comes from here. And then you can also check for yourself. There'll also probably be fragments for something like this as well. So this fragment is 16 plus 12 plus 12 plus 3. So that's going to be 30 plus 36 plus 2 plus 2 plus 3, which is 43. Okay, so this fragment on the right is 43, and then you also have oh wow, they're both 43. I didn't realize that. Okay, so no wonder that fragment is so, no wonder that's the base peak. Then you can make a sneaky answer in your response and say no wonder 43 is the base peak, because if you split it halfway, both signals show a mass to charge ratio of 43. Okay, so that's 43. If you split it another way, you'll probably get the other fragments as well, but that's just to confirm. Yeah, so this is your answer.